just record this. So you take your standard error, and with that value, you calculate, for one, you standard deviation over the number of samples in your sample or your population. So if you're looking at a data frame, you're counting the number of rows or the number of values in that list that you're going to calculate a standard error from.
Right.
So for any list of numbers, you take that standard deviation divided by the square root of the number of errors.
Okay.
And so the number that we talk about that you use to calculate your T star, or like that critical value, comes from the process of taking your number of values, essentially these numbers on the left, and calculating that against the sigma or the significance level that you'd be interested in using.
Okay.
Generally speaking, 0.95%.
Okay.
So that's the only part where the metric, like that's where we get those numbers 1.97, or that value that's approximately around 2 standard deviations. Because it's not exactly 2 standard deviations, there's a little bit of that. There's a little bit of a change depending on how many numbers. But generally speaking, you can expect that number to be close to 2.
Okay.
So when you take that number, that's where we go back to the concepts that are in the notebooks. Where did I leave the material from the notebook? What was that? Did I close my notebook materials? Whoops. Let me just make sure. Oh, no, it's because I was using someone else's notebook. That's right. Okay. That explains that. So once you understand that the standard error is essentially just part of the calculation you use to calculate that margin of error, that's where this value comes into play. So if you look at this symbol here, that's the same as our equation for standard error.
Wait, give me 1 second. Yeah, because I was looking at something else. Yeah,
Okay.
sorry, what up?
So this
Okay,
equation, yeah,
right.
This equation is the standard deviation over your number of samples. That's the
Right.
same as this equation.
Okay.
Yeah, and you use that plus your critical score to estimate or calculate the margin of error.
Okay.
Now, the margin of error is the value you use to create your confidence intervals. Sometimes they're used synonymously to define kind of like the same term, but really the margin of error is the range of values between your location value and your lower and upper confidence intervals.
Okay, and the confidence intervals that's not a significance. That's not a significance level. That is so significant. The significance level will be 0.05, and the confidence interval will be 95%, right?
Correct. So the significance level is your cutoff value for when you reject or fail to reject your hypothesis value, your null hypothesis.
Right.
Your confidence interval is when you take that same significance level and create a series of confidence intervals to which you can speak with 1 minus your significance level, in other words, 95% confidence, that were your frequency going to be calculated many times, that your population mean would fall within that range between that lower and upper confidence interval for the population mean.
Got you.
So let me see if I can show you as an example.
I was hoping that.
Yeah, we've taken all of these different values. We understand that we calculate our margin of interval. We still have our critical score. Let's move away from that.
Real quick, now the margin of error, could we, is it a a stats scientific method, like like the same as like the t-test sample? Is it, could we calculate it like with SciPy?
There should be a package that I may need to look up to remember exactly which one it is. But the method we talk about in class to show you how to calculate that population level is the percent point function, which what this does, it essentially takes a look at the number of values you're working with and returns that T star value. When you take that T star and calculate it against your and calculate it as part of your calculation for your margin of error, you're essentially taking that T star value, multiplying it times your whatever your standard error is going to be, plus or minus your average. So this is your calculation that you're looking for to determine your lower and upper, like your lower and upper value. Or otherwise, if you want the margin of error, just the margin of error, you take your T star times your body times your body standard error. So let me go ahead and run these previous cells and show that what it looks like beforehand. Okay, this value calculates your confidence intervals, your lower and your upper band, but this critical value, T star times body, it tells you in which direction upper, like above and below your mean, your margin of error is going to be, or where that confidence interval is going to be. So in other words, this is your margin of error, 0.07. With me so far?
Yes. Yeah, yes and no. But then yeah,
Okay.
I would have to just rewatch the video again.
Okay.
Yeah, but then I do understand the concept now. Before I was a little bit in the woods, but now it's it's
Okay.
sinking.
So yeah, I mean, how should I put this? This is a value that gets calculated mathematically. If you are trying to, like, the reason I show both the PPF version to grab your critical value first is because the T interval essentially returns the confidence interval for you, as long as you have these different features ready to go. The location, you essentially take your alpha, your the degrees of freedom. In this case, it's what you want to keep track of. I know it's, DF can get mixed up with the data frame itself. Your starting value in a distribution and the scales to which that measure takes place. The rest of it, the T star, gets calculated as part of these two arguments from T interval. But if you're looking for SciPy margin of error, let me quickly check. That's still standard error. Yeah, that's still just true. It returns a standard error here.
Right. So yeah, so you were explaining the confidence interval.
Sure. The question is, you want me to explain what the confidence interval in this case?
No, because you were explaining. I lost my train of thoughts now. Because you were explaining. Oh my God. Whatever. I'll go through the video again.
Okay.
Yeah, it's just so many concepts that it's just hard to kind of
Gotta sit
change.
down.
Yeah.
Okay.
Anyway, yeah. Hey, what's up, Hamid?
Thanks.
How's it going? How you getting everything?
Surprisingly, yes.
Oh, wow. Yeah, I need to partner
Maybe
with you.
that's like 1% chance out of 100.
Right.
Well, the fact that this is a quieter office hour is probably a half decent sign. I'll probably reach out to folks after I see what the grades look like in your module projects. The tasks too tend to be a little bit more by the book for this exercise.
Yeah, I don't have any more questions.
Okay. You take a look at here for a second. Start perfect. Okay. Okay. The other concept that tends to get tricky is the confidence intervals as far as what to do when you want more or less wide confidence. I can go into that next. This is body temperature. Histogram. Temperature. Typo. Okay. Any questions you might be coming up with so far?
Well, I have formulated a question from our earlier discussion. In a 2-sample t-test, it feels to me like there's a lot of moving parts. There's not just the 2 t-samples. There's not just the 2 samples. There's a greater body of samples. So I guess I'm confused. If we have a greater body of samples, why would we be measuring 2 samples off each other unless we wanted to know something specific about how the 2 samples related to each other?
Correct. So what we're trying to do is measure if there's a significant difference between 2 samples. To a certain extent, like we can recognize that all runners from the without having to go into the example from the homework, but in the example that we saw earlier,
I mean, that'd be fine.
That's the runners example. Yeah, let's go ahead and
Yeah.
take a look at that. Let me just pull that up, bring it by my line. So I'm going to take this from the assignment and add to this at the very end. I didn't know called office hours. Ouch. Right. Take that code from class. That's the Disney. Then it has us going through runners. Just grabbing code here willy-nilly. Yep. This is going to be in the notebook that's currently attached to class, so you can always go back to that.
Okay.
So this is your racers for the male racers. So if you calculate the average time for male and female, just going to take a look at both values. Let's create one for the full rate for the full set of runners. Whoops. Yeah. Disney. Their racing time. Full group. So when you look at the average, what we've got, what we're looking at here is the question of whether they are potentially from the same population. Or what's the probability that both of these groups would be from the same population?
And
Mhm.
does that mean something different than, or does that mean like we already know they came from the same sample
Mhm.
of run times?
Mhm.
So I guess, is that what that means? We
So-
already know, we
So
want to
what
know
it,
if they come from the same.
so it's possible that the two means could come from the same population and have, a little bit of a difference. But what we're trying to look at is what is the probability of whether these two sample means are this like equal enough to each other to be considered as part of the larger population. Now we understand that, but we just want to know how significant it is. As like we're trying to determine if the difference within that population is significant enough to it just being for there to be a meaningful difference between the two, racers, between male and female racers. So
Okay.
yeah, so it's more about, you look at it, you can look at it from multiple parts. Like there's the probability that there are two different distributions and two completely different distributions. We can also determine that there's a probability that they came from the same distribution and they're just close enough to each other. So it's essentially like you overlay this larger population over these two smaller distributions and determine which of those values you essentially return results from. So let's take it from step one before we go into that. We have these two racers and we're trying to determine, hey, is there a significant difference between male and female runners given this specific population? Or this specific this specific data set from this particular population. In order to demonstrate, say what we're trying to look for is a specific difference, or we're trying to measure if there's a difference, we measure that as our alternative hypothesis. Because anytime you're running a two sample independent test, you're essentially working off of the presumption or your null hypothesis that both male and female runners are going to be part of the same population. That ends up being your null hypothesis. When you run that as one of the tests, so from SciPy stats, let's go ahead and just import the tool directly. T-test independent sample. What we're running, even as an object, it's just looking at that t-test for these two values. And it's the null hypothesis might have the same expected average. Because if they were from the same population, we would, according to the central limit theorem, because these are two samples that independently were taken from the same population, we can expect them to have the same mean. Now we're looking at this and we can already see that they don't seem to have the same mean. So let's see just how different this is. Finish, female finish. And this is where things get a little bit interesting. Because what this is saying is that even though the running time is from the age bracket is the same, like the running times do come from that same population. The fact that they are two different groups, they have that additional variable of being male or female. Those two specific groupings mean that independently speaking, these still could be considered part of two different two different distributions. So although the times are from the same area, because we split them up into two separate populations, we now have a difference between the two groups.
Okay, thanks. That's making a lot of sense.
A little bit, yeah. It's tricky because we introduce one thing right after the other.
Yeah.
But because our p-value is so small, like essentially that's where we reject the null hypothesis that these both have the same average or have the same, like could potentially be in the same distribution. Are we clear on how p-values work, the wider and the narrower? Okay.
Sorry, I'm interacting with a 4-year-old as
Yeah.
well.
Yeah, that makes sense.
My understanding of p-values is not comprehensive, but
Okay.
I'm not sure that's I don't think that's true for Hamid. Sounds like Hamid's got it.
All right. Awesome.
Well,
To nod. Love it.
P-value is actually very confusing for me too.
Oh, really?
Say that again. I'm sorry.
P-value, understanding the p-value, because it's written in a sentence which is hard, especially for me as a
Sure.
English as a second language.
Let's do this.
What I understood from p-value is it's the likelihood of getting a wrong decision. So if that likelihood is more than 5% to be wrong, so we fail to reject the null.
Yeah. Another way that you can think about, or another way that I think helps me think about it, is if you look at a normal distribution, what section of, let's say you just reach in and just grab an individual value from this histogram, which area are you the most likely to grab a value from? Yeah, like this middle area, right? Yeah. It is less likely that you would end up grabbing a value from these corner values. And as a matter of fact, you can quantify, there's a section of those tails where it is less than 5% that you'll get either one of these two sections. Like, so if you grab in and reach a value, the chance that you grab a value from those two spots in red is less than 5%. And that's what we're, sorry, go ahead.
And that relates to our confidence level too, right?
Correct. Because we essentially determine that if we want to draw an inference about a larger population, given the data that we have, we can use those same principles, except it's just referred to as 1 minus your significance level to define confidence intervals for the larger population. So what you're doing with your t distributions, or what you're doing with your p-value, is you take a sample, like, and now, okay, this, like my example, I cited this with like individual values, but if we pretend that these are a collection of sample means, all of this is a distribution of sample means, by default, we can apply the central limit theorem to understand that the central limit theorem is that if with enough samples, with enough sample means, you'll have a normal distribution. And so if your sample mean ends up being something like 97.2, you know that it's inside the area where the probability is that it's part of your general population. But if your sample mean just happens to fall, for example, on this line out here, it means that your sample mean of 99.8, for example, falls so much on the outskirts of your distribution that it's not unlikely to be part of that population. or it doesn't fall within the distribution that would be needed to be correct in order for the null hypothesis to be correct. So in other words, if your null hypothesis is that the average human body temperature is 98.2 in this graph, and you end up with a result that's 98.7, that's still close enough to 98.2 within this distribution, within this given number of samples, for you to fail to reject that 98.7 would be significantly different from 98.2. That's not the case for 98.6 up here above, because that one's so widely different from your population average of 98.2 that you can say it is statistically significant that this value is different enough statistically that you can reject your null hypothesis of the population average being 98.2. Or that you can reject that your sample size would be not significantly different. That was adorable.
This is Rainbow Dog.
Hi, Rainbow Dog. Oh, that's cute.
Do you want to say hi, Hamid? That's Hamid down there, and that's Julian up there.
Hello.
Hello.
Hey, hi. Oh, here's a good article that sort of goes into some of this. Let me show this on the Slack channel. Ooh, that sounded rough. All right. Next questions. Any questions about the assignment?
I had a question about the p hacking.
Yes.
Is it like, how common is it in the practice, or like I read somewhere it's not okay to do p hacking because we selectively select the significant p value?
Yeah. What you want to do is understand that p hacking it's easy to catch because a simple statistical test will determine whether this value makes sense. I've actually got an example somewhere of what it looks like in action. It's not it. Technical practice or some progress works. One sample t testing, is this it? Might be it. Yeah, okay. All right, so we've got a bunch of different modules here to run through. But what I want to show you is this for loop. So what this for loop does, you take a series of samples from your values. Visualization's not pop up. There we go. All right. We'll do this for a little bit closer of a short, smaller p-value. All right. So here's a t-test one sample test that takes so in this case, your population is going to be the Titanic. Yeah, I know there's a lot of code, but for the most part, I'll make sure to show you what you need to look at. So your distribution for the Titanic, as we've seen before, essentially skews right because there are some older individuals who take the Titanic age a little bit higher. You take a sample of those values. In this case, I took a sample of 10 rows, and you calculate that sample on a distribution of 40 rows. You still see that it sort of skews to the right, but you now have fewer samples. It starts to become a little bit more normal. You can also see where the average changes a little bit. So what I'm intending to do is demonstrate. If you take random samples, in this case, 20 samples from your population of Titanic age, I broke them down into 40 individual samples, and I return to count the average, the median, and I run a t-test that takes a look at all of those individual samples. Remember, I took 20 samples, 20 different samples, and calculate them against a one sample t-test against the whole population, that reference value being 29 point whatever it is. If the p-value is greater than 0.05, you fail to reject. Otherwise, you reject your null hypothesis. Now, here's the thing. Our one sample t-test tells us, and like most of the rules of any distribution, is that we understand that taking samples from a population, that average should, for all intents and purposes, still be measured as part of the, like, the question we're asking is like, is this sample part of that larger population? Is the sample value, these 40 samples that I took out, are they part of that Titanic age population? The answer, as far as we know, yes, we took those samples directly from the population mean, and that's what we're testing against. So if you run this, you scroll down to the end of this. I'm going to scroll down to the end of this value. This will return a list telling me how many times I rejected the null hypothesis. Remember, if I reject the null hypothesis, what I'm saying is this sample does not belong to this population. Remember how we started? Obviously, the sample belongs to the population. But what I'm seeing from this number 12 is that if I look at the image for test number 12, so it's telling me that the sample mean, 22.9, is not part of the Titanic age distribution. We know that's incorrect because we took it directly from that population. But out of 20 tests, 1 was incorrect. And that lines up with how we talk about these 20 tests, because we took 20 samples. For all of those samples, the population mean was indeed part of that sample area, but not 1. So we got 1 in 20 as a mistake. I'll run this again just so that you see the results again. 20 different distributions from the same distribution. In this case, it was number 14. If you take a look, see, it's a mean and a median that's much higher, 37 and 33. So p-hacking would be my saying, I rejected my null hypothesis, even though that was the only time that my test rejected the null hypothesis out of 20 tests.
What is the significance of sample 40? Because I see range 20.
Yes.
I initially thought sample 40 was, what is that?
That
So
is
each 20 is we're going to do it 20 times.
so sampled 40 is that you take from a data from you take from a string of data 40 samples. So you take it as, yeah, so it's like
40 samples 20 times.
Yeah, so I do what happens is do this 20 times, take a sample of 40 values from the Titanic age, run that sample mean against the mean and the median, and run that against a one sample t-test. So the results of that one sample, run that as a one sample t-test against the mean of the Titanic age. Run through this evaluation. And then once that initial loop is done, go back to the very top and do it 19 more times. I can share this bit of code.
When I took that Python course in November, it was like we used loops all the time. So I was excited to see this.
This one's fun. I don't know if I showed this one in the video.
No, I don't think
Okay.
so.
All right. Hamid, did that answer your question about p-hacking?
Yes. My next question is, so I don't know how to phrase it. We are not always looking to a significant p-value if the research is supposed to be very, very similar or close to the population. Like we would say that even the result fail to reject the null, though they are not published, unfortunately. My question is, if we do p-hacking, so we will find like a significant p-value. And isn't that a bias, a kind of, because we are just looking for the significant p-value?
Mm-hmm. Absolutely. So there is a certain, so the reason this method gets, the reason we warn against p-hacking is because when you're working with statistics, you have to specifically recognize that there's going to be a certain percentage of your results of your values that you're going to be incorrect. Given any type of statistical test, there's always a possibility. In this case, we measure what that probability is that you're going to be incorrect. So then it ends up being based on the tests you're running, how frequently is it okay for you to have an error or to have a mistaken value? So in this case, what we run when we run our t-tests is that if you run this test an infinite number of times, you can expect there to be a 5% chance that you incorrectly reject your null hypothesis. I think the example I've used previously is that if you are trying to calculate the probability that a certain service is working for and this tends to be a little bit more when you dive into categorical values, but if you alter your values for your significance values, what you are altering is the probability of how many of those results that you get are going to be incorrect. So if you're doing kind of mail orders, if you're doing like advertisement on a wide scale, it's more likely that you're going to want to operate on a more wider confidence interval, because if you accidentally advertise to the wrong customer, there's no harm in that scenario. But if you were to be working with, something for a new antiviral medicine, you want to make sure that there's a certain safety element to the medicine that you're administering. So you might want to operate with a much more, you want there to be less room for error. So you would likely navigate with a more narrow confidence interval.
So I think so. That's is the alpha 5% is because we might be wrong 5% of the time.
Right. So the alpha of 5% is a very arbitrary standardization. There's plenty of debate to argue why you want to keep to Fisher's 0.05 significance level. Depending on the industry, like that can change. So 0.90 is acceptable in marketing, 0.99 is more acceptable in a medical field.
Thank you.
It's like cherry picking, right? P hacking.
To some extent, exactly. Yeah.
Fell in the margin of error.
Mm-hmm.
It would never survive peer review.
Right. But in certain Kaggle competitions, you can essentially submit the sample that you know, the Kaggle, like in the early days of Kaggle, like you could just submit the sample of your test that returned the best results through p hacking. That is like Kaggle's competitions now have a few metrics in place to prevent p hacking. What other questions do we have?
I guess I have a question as to, are we going to be working with all these concepts all week, or are we going to be adding more on top of them?
So tomorrow we add how to do the same process with categorical variables. In other words, we take a set of values from the same concepts will apply. We're looking for p-values in different distributions and in the areas under curves. So we take a look at, today we take a look at how this works with the normal distribution. Tomorrow we look at what this looks like with a different chi-square distribution. So it's a little different, but it's the same principle. It's like, how much space do you have underneath the line to get a percentage of 5%? Chi-square is a little bit more straightforward because it's just conditional probabilities. On Wednesday, it turns around a little bit and we go into an introduction to Bayes' theorem, which is a little bit of a different approach to administering or considering statistics. Like, the thing about p hacking is that there's a certain extent of like, you're constantly running tests. The idea is like, if you run 1 million tests, what are the probabilities that you'll get these results? Whereas with Bayes, a very much approaches, if we run this test, how much can we expect our results to change after the test has been run? After we run the test with the data that we gathered. It's trippy.
Yeah. The amount of things that we learned for today is like, I wouldn't have been surprised if that had been a Thursday.
I'm probably going to review some of this again tomorrow because I didn't like not being here today, but I really can't, like, I'm still typing hurts. So it'll be fine by tomorrow, but like, yeah.
Yeah, ouch.
I'm so like, let me go ahead and turn off because nobody needs, I don't need to share my shame on record, but like, yeah. So why is this important? The importance behind this is that at the end of the week, we dive into our first predictive model with linear regression. And as part of that process, we take the models we get from our linear regression, and we are able to determine and incorporate confidence intervals. So we're able to we can essentially go on to say that the slopes from our linear regressions can be modeled as part of a larger population. It's cool stuff, but All right. Any other questions? Otherwise, I'm going to let you all go.
No question. Thank you.
Chat with you soon.